Okay, so the second mini exam is due today. So if you have that for me, I'll take it. Make sure it's stapled, your name's on it. Okay. Anyone else doing the second one? Any other takers there? Did I give you all enough? Do you need one more? So the third one, the third exam, I just handed out. And come on. The instructions on this one are a little bit different. So first of all, it's due in 1 week, so there's less time. I'm also asking that you work alone on this one. So I do not want you working together. I do not want you in the tutoring lab getting help. I want you to come to me, call me, text me, whatever, if you need help on this, all right? There's 4 questions. Yeah. Okay, so this mini exam, the problems here are out of chapter 10, sections 7 and 8. All right? So I would take a look at that. I wouldn't wait too late on that one. There's some somewhat I'm not going to say challenging, but there's some interesting integration that has to take place in this exam. So okay, and speaking of which, I realized that when I did chapter 10, section 7, when we were doing vector functions, I had talked about derivatives of vector functions. We talked about how when you take a space curve, a vector function, you take its limit, it's real easy. You just do the limit of each component. And when you take the derivative, it's real easy. You take derivative of each component. And there's nothing crazy. And we defined velocity and acceleration. And then I got to this slide, and usually that slide right there makes me think, okay, that's the end of the section, and I just moved on. But there's actually an entire other piece here that I didn't cover. So I need to cover this if you're going to be able to do that assignment, and that is integration of vector functions. And again, there's good news. When it comes to integrating a vector function, so please remember we are back to 10.7 now. We have a vector function, r of t, that has 2 or 3 components. If we want to integrate the vector function, then we're going to integrate it with respect to t, because t is our independent variable. And then we'll have limits of integration a to b. And again, it's real nice. If you want to integrate a vector function, you integrate each component function with respect to t. Take your limits of integration. Everything's nice. All right, so no surprises. So we can do a quick example of how to integrate a vector function. So if we're going to integrate this, let's first see if we can't integrate it without any limits of integration. So like back in Cal 2, you have definite integrals versus indefinite integrals. Indefinite is when you didn't have a limit of integration. So if we were to do this, we would be wanting to take the antiderivative of e to the t dt. That would be the first integral we have to do, and then comma, now the antiderivative of t root t minus 1 dt. And then finally, we would be doing the antiderivative of natural log of t dt. And notice that our answer, we're going to get some function here, some function here, some function here inside the angle brackets. So our answer is going to be another vector function, right? But we're going to run into one problem, and it's the same problem we ran into in Cal 2. If you're doing an indefinite integral, then you can only get an answer within a constant. You always had that constant of integration, didn't you? Same thing here. We're going to have an answer that's within a constant. And we'll talk about how we're going to use this in a second. Let's just do the mechanical part. So the first one's pretty easy, right? Antiderivative of e to the t will be itself, right? So we're going to say that we've got e to the t plus a constant. So I'm going to say plus c1, and the reason I'm using c1 is because I'm going to have 3 constants, right? So I either need to use like C1, C2, C3, or maybe you want to do like plus C here, plus D here, plus E. I wouldn't use E. E is a number, right? So you start to run out of letters, I guess, at some point. So I'm just going to go C1, all right? That was easy, right? That antiderivative. What about the next one? Yeah, so I'm going to do that over here on the side. If I was doing this, then I would have T root T minus 1 dt. I would do a U substitution on this one. Real quick U sub would be, what are we using as our U sub? T minus 1. And this is one of those ones that the U sub, it may not look like U sub at first, but when you do U sub, it works out. So U is that. Everyone has learned integration kind of different way. You then take the derivative of this, so I would just go du is dt. And then what I taught my class to do is you try and rewrite the integral in terms of u right now. So I'm going to replace, anywhere I see t minus 1, I'll replace it with u. I replace dt with du. So that's going to become du. This is going to become root u. But I still have to replace the t. And how do we do that? Yeah, just solve this equation for t. So if we solve that equation for t, we get t is u plus 1. And the good part of doing it this way is that that new integral will become t, which is u plus 1. That's in parentheses. And then square root of u, which I'm going to write as u to the 1/2. And then dt becomes du. And so it's nice. Now what you can do is you can distribute the u through the parentheses. You'll have, u to the what? 3/2, and then plus u to the 1/2, and then all of that du. And then you can do these term by term. So just power rule on those. So what's the antiderivative of this? You add 1 to that, you get 5/2. So we're going to put in front of it 2/5 u to the 5/2, right? Okay, so this will become 2/5 u to the 5/2 plus, and then we do the same thing on the other one, 2/3 u to the 3/2. And then we should have plus c, right now, but I'm going to call it plus c2. And then we have to go and replace all our u's with t minus 1. So I'm going to start writing this out here. This is 2/5 t minus 1 to the 5/2 plus 2/3 t minus 1 to the 3/2 plus some second constant of integration. I forgot my, no, I did forget my comma. There's a comma right here, right? Okay, there's a comma there. I thought I had written it, but that was C1, not my comma. And then now another comma. Now I have to integrate this last one. And so how do we integrate natural log of t? You're either going to have it like memorized, or I don't know, depends on how you did it in Cal 2. For my classes, we derived it, and then after that we wrote it on our formula sheets. We were allowed to use that. But how do you take the derivative of that? Antiderivative. How do you find the antiderivative? Natural log of t. Remember what technique you use? Integration by parts. So again, everyone's got kind of a different way that they were shown integration by parts. The way, again, that I show my classes is I always have them make a table. And with integration by parts, we're trying to do the antiderivative of u dv equals uv minus integral v du. We're using that formula for integration by parts. And so what I do is I have my students make a table. I have them, this is where they get to choose. They have to pick which part of this expression is going to be u and which part's going to be dv. And in this case, you really only have one choice for u, and that's natural log of t. So you put natural log t here. dv then has to be the dt part, and then I have them finish the table out. I have them differentiate down and integrate up. So we differentiate down, du is 1 over t dt. And if you have your own way, that's great. Yes?
So whenever you're doing that, like I'm sure you've seen this, the like Day8 and Day8, right? But there's like exceptions to that rule, so.
That's why I don't teach that rule. I don't like it. I don't like exceptions.
Oh, so like on this, you can just you just pick whichever ones you want to be U and D.
You can't know. Well, you have to pick. You have to pick. You have to pick, right? Which of these it is, but it's not. I try and get my students to think about what is the new integral going to be. Okay, what is your new integral going to contain in it? V du, right? So it's going to contain this diagonal. These two functions right here are going to be in the new integral. Okay. So if you put dt up here, then when you differentiate it, you're going to get the second derivative, which, no. You know what I'm saying? You're going to have the derivative of the derivative. And then if you put ln here, natural log of t here, what's the first step you have to do? Integrate it, which was the original problem. And if we couldn't integrate it to start, we're not going to be able to integrate it here either, you know? So there's kind of like a thought process that I like people to go through rather than like a, what is that, Day8 or something like that. Yeah, I just don't go with that Day8. Day8 works a lot, but I think, just my opinion, I think it takes away from the process of actually thinking through what's happening and choosing an educated guess as opposed to just, I'm going to follow the formula, you know? Logs. I don't even know what it is. Logs, inverses, algebraic,
something with
t, trig, exponential, right? And there's less thought involved, so I don't know if that helps. Am I addressing your?
I mean, I'm just confused by that.
So, you're confused by how I chose these? Did I clarify now a little bit why I don't want to do it the other way around?
I think a little bit, yeah.
Okay. Because I can, whatever I choose for u, I need to be able to differentiate it, which I can. Whatever I choose for dv, I need to be able to integrate it, which I can always take the antiderivative of dt back up to t. So it's just, it's kind of natural for me to put it this way. All right, so v here is t. And so the new integral, right, this new integral becomes u times v. My students, how many of y'all learned the ultraviolet minus voodoo? Ultraviolet minus voodoo? It sticks. I mean, I don't know. It was taught that way to me. Ultraviolet minus voodoo. I don't know. It just. So I'm going to do ultraviolet first. This right here. So this is t ln t minus now integral of voodoo. But voodoo is the diagonal like this. And that's a really nice part to have here. We'll take that here. And that, what does voodoo turn out to be when you clean it up? Just 1 dt, right? So, and that's easy to integrate, right? That's just going to be t. So we have, I think we have our last function here, don't we? T ln t minus t plus some third constant of integration. And we're done. So that is your general antiderivative of that vector function. Now we are asked to find the integral from 1 to e of this. So we actually wanted the definite integral, right? But I knew it was going to take some time for us to get a few of those, so that's why I did indefinite integrals first. So how do we do the definite integral then? If we're going to go from 1 to e, let me erase some stuff so I can have more room. If we're going to go and do the integral from 1 to e of r of t dt, then that's going to be each of these component functions, right, evaluated at the two different limits of integration and subtracted. So this is like your capital F of b minus capital F of a, right? So I have to take this vector function and plug what into it first? E, and then subtract from that this plug with what plugged in? 1. Now remember, the constant of integrations, they cancel out when you subtract. So when we do the definite integrals, these constants won't matter anymore. Right, so let me do that first one. It's going to be e to the, you said it was e to the e The constant's going to cancel, so then e to the 1. That's the first piece, right? And then I have to do the same thing here, right? So it's going to be e minus 1 to the 5 halves times 2/5. So 2/5 e minus 1 to the 5 halves plus 2/3 e minus 1 to the 2/3, 3 halves, sorry. 3 halves. That's what I get when I plug in e, right? And then minus what?
When you plug in 1, all of the parentheses.
All the parentheses go to 0, so that's zeroed out, that's zeroed out. So there's nothing there for the second part. And then finally, last part, we plug in e first. So we get e natural log of e minus e. So e, what is natural log of e?
1.
1. So that's just e, isn't it? Then minus e is 0. So I don't need to write that. Okay, I can get rid of that. And then when I plug in 1, I have to subtract, right? I better put the subtraction sign here. I'm going to subtract, maybe I should, I'll just write it all. E is what we got minus e, and then we're going to subtract from that whatever we get when we plug in 1. So we get 1, natural log of 1, and then minus 1, like that. And that would be 0. This in here becomes what? That's just negative 1 because natural log of 1 is 0. So this is negative 1, but then minus, so plus 1. So your last component here actually turns out to be just 1, right? And then these are just numbers, whatever they are. Okay, you can just leave it like this. This is just some decimal, right? You could get on your calculator and figure out what that is. You get on a calculator and figure out what that is. But you're going to have a number, right? It's going to be a number. Well, I should say each component is a number. Your answer is a vector, but each component is a number. All right. Understand how it works? So there's nothing new in terms of there's no new secret integration that you have to learn or something. It's just now you're putting it into the framework of a vector function instead of what you did in Cal 2. All right, now there is a result that we have from this that is very similar to what we had in Cal 2. Yeah, let's do this one first. Okay. I don't want to integrate that, but I guess we will. So look at this one. This one says find r of t, all right? Find r of t, and they're giving you the derivative of it. But they also give you one other piece of information. What is that telling you right there? What does that information mean?
When t equals 0, all of these equals 1.
So when t equals 0, right? When t equals 0, the position of your, if we imagine this being like a particle moving through space, this is saying at t equals 0, this is the position of your particle, 1, 1, 1, in three-dimensional space. Right, like a vector. But so they're giving you the derivative of the vector function. They want to know the original vector function, and they just give you one piece of information about the position, which is this. So remember, when we integrate, we get constants, right? This piece of information is going to help us actually find what those constants have to be. So let's see how this works. I need to find the antiderivative of r prime of t. And that means I want the antiderivative of each of its pieces, right? This should be r of t, right? R of t should be the antiderivative of the derivative. So antiderivative of t dt, antiderivative of e to the t dt, and then the antiderivative of t e to the t dt. All of those. So some of these are easy, right? This first one is what?
T squared over 2.
Yep, t squared over 2, or 1/2 t squared, plus a constant of integration, c1. The second antiderivative is e to the t, plus again some constant of integration, call it c2. And then this one is not so clean. You have to do that on the side maybe. Integration by parts again, So if I were doing integration by parts, the way that I choose which goes where is when you first use integration by parts, when you're first learning it, hopefully you're taught that what you're doing is when you go from this integral to the new integral, that you're going to be doing what's called transferring the derivative. So one of these you're going to take the derivative of, one of them you're going to integrate. And what you're thinking about is what looks nicer in the new integral. Would it be nicer to have this one differentiated and that one integrated? Or would it be better to have this one differentiated and that one integrated? So let's consider both ways. If I differentiate that, that's what? 1, right? There's 1 dt. And if I integrate that, that's just e to the t. So I'm just going to have 1 times e to the t. That's great. I love that. If I do it the other way, I differentiate that, I'm going to get e to the t. That's not a problem. But if I integrate that, I'm getting 1/2 t squared. So I don't want 1/2 t squared and e to the t together. So the first way is preferred. So t here, and then e to the t dt is the other part. And now we just, okay, so down here du is dt, and then up on this one is e to the t. And so this becomes ultraviolet minus the integral of Voodoo, which are these two. And so at the end of the day, we get t e to the t minus e to the t. And yes, you could factor out an e to the t, but I'm just going to leave it like that, plus some constant of integration that I don't know. So this is r of t. I know what the space curve function is within these 3 constants. I don't know what those constants are yet. But now I use this information that tells me that if I plug 0 into this for t, it should spit out 1, 1, 1, right? So the fact that r of 0 gives me the vector 1, 1, 1 implies that when I plug 0 in here for t, here for t, here for t, I should get the vector 1, 1, 1, right? So that implies that, let's plug 0 into this. What do we get here? 0 for t, we get c1, right? 0 here, we get 1 plus c2. And 0 here for t, we get, so that's 0, that's e to the 0, negative 1 plus c3, right? Make sense? That must equal the vector 1, 1, 1, right? And therefore, you can match up the components. This is just 3 equations. This must equal this must equal this must equal this. So I think we can do it without even looking here, without doing anything other than looking. Yeah, okay. So what's C1 have to be? 1. C2 would have to be 0. And then C3 would have to be 2. And so what we can do is go back to get our final answer, because this is not our answer. Our final answer would be rewriting this r of t again, but now replacing these constants with what they are. So we have 1. This one was 0, so I can just leave it as e to the t, and then this one has to be 2. So this right here is the vector function that has this as its derivative, and at 0 is 1, 1, 1. So we have a unique solution now, don't we? Instead of having like a family of functions with all the plus constants and stuff, we now have nailed down the precise function that we're talking about. So does this all seem like the same stuff from Cal 2, just in a different form, pretty much? Okay. All right, so some things that we should note here, that just like we would expect, if you start with an acceleration function, all right, which tells you the acceleration of the particle at any point in time, then the velocity function can be recovered by taking the antiderivative of the acceleration. And then if you take the antiderivative of velocity, you'll get the position function. But we know that every time you take a step backwards, every time you integrate, you get a family, right? So if you go from this backwards twice, you get, what do you call it? You'll have like 2 sets of constants in each integration. Or sorry, 1 set of constants for each integration, so 2 sets of constants. Off the subject. Well, on the subject, but off the subject. I wonder how many of y'all saw this, because I think this is a pretty amazing fact. Do we know that on Earth, if you drop an object, the only thing acting on that object is gravity, right? I mean, let's take the air out, okay, because the air gets complicated. But you go to any planet, that planet has gravitation on it, right? Depending on the mass of the planet, where you're standing, you'll have a certain acceleration of gravity. Do you know what the acceleration of gravity is on Earth?
9.8 meters per second squared.
So you heard this, like negative 9.8 meters per second, because it's acceleration, right? What is that in feet per second? Does anyone know what that is?
32.
Let's see. Yeah, let me ask Google. 9.8 meters per second to feet per second. Oh, it didn't let me finish. 9.8 meters per second to feet per second. 32.1. Let's round it to 32, okay? 32. This is approximately 32 feet per second squared, all right? Meters per second squared versus feet per second squared. So what if I tell you right now that the acceleration, and don't think of vector functions, just act like you're back in Cal 2. What if I tell you the acceleration of an object is, negative 32 feet per second squared? Then what's the velocity function? So what's velocity? Well, you have to take the antiderivative, right? So what's the antiderivative of this with respect to t? Antiderivative negative 32 dt would be, what did you say? Negative 32, I'll say t, because we're using t, could be x, plus some constant, right? Agreed? And then if I want to know the position function, which I'll just call s of t, position, I have to do the antiderivative of that again, right? Yep. So if I do the antiderivative of that, then I'm going to get what? So that's going to be negative 16t squared plus c times t plus some new constant, which I'll call d, right? Okay. Now, this right here can be rewritten like this. And that's the way you'll see it in like a physics book. And this is your position function for falling bodies on Earth, right? And what this says is that if you give me the initial position of the object, so when time started at t equals 0, how high was the object, right? So let's look at our function right here. Let's look at this one right here. If I plug in 0 for t, right? What's the only thing left? D. So that's got to be at time 0, d is my position, right? And then what about in terms of velocity? What would my initial velocity be? We come back here, look at velocity. If I plug in 0 for t, we would get what? C. So this coefficient and this coefficient are actually your starting height and your starting speed of your object. And this is the parabola that we use to determine the height of an object off the ground at a certain, well, at any point in time, right? You just have to give me 2 things. Does that look familiar to you? What I've always found fascinating about this is you take me to a different planet and all that changes is this, right? So on a different planet, this looks exactly the same. The only difference is that coefficient. That's the only number in the entire problem, the entire equation, that changes if you go to a different planet. That one right there. Kind of cool, right? All right, anyway. All right, so if we're dealing with the vector function, right, these things hold. So antiderivative, same thing. We're going to have constants we have to worry about. So look at this one right here. Give you a of t, and I give you some information about the object's initial position, because r is the position function. So I tell you at 0 it's this, and then I also tell you that the velocity at 0 is that. So let's get this thing started. We want to find the original position function. So I start with a of t. Let's find v of t first. To find v of t, we take the antiderivative of a of t, which, with respect to t, which is going to be, we have to do the antiderivative of each component function, right? So the antiderivative of t dt, the antiderivative of e to the t dt, and then the antiderivative of e to the negative t dt. And this one's nice. There's no integration by parts or anything. These are all nice antiderivatives. So what is our velocity function going to be? 1/2 t squared plus some constant, right? And then e to the t plus some constant. And then finally, negative e to the t, negative t, right? The antiderivative of this is itself, but you have to account for the chain rule. So if I took the derivative of that without the negative, it would be itself times -1, but I need to kill off the -1, so I need a negative out there, right? And then plus C3. Okay, now what?
Plug in the v.
Yeah, we know what v of 0 is, right? So v of 0 being the vector 0, 0, 1 implies that when we plug 0 into this for t, what would we get when we plug 0 into this for t? C1, and then 0 here, we get 1 plus C2, and then we plug in 0 there, so what's that going to be? -1 plus C3. That must equal what? 0, 0, 1. And so now we can solve for each of these. So C1 is 0, C2 is -1, and C3 is 2. Is this good or no? You all right with this? So what we can say now is that our velocity function, we've nailed it down exactly to one function and one function only. It's this plus 0, so just 1/2 t squared. And then this one -1, so e to the t -1. And then finally the last one, which is this one, negative e to the negative t plus 2. And we're like halfway there, right? Now we have to integrate that again, and then we'll use this information. Does this make sense? Should I continue, or you think you can go the rest of the way? Okay. Just remember when you integrate this constant here, right? Antiderivative of 1 is going to be t. That's going to be 2t. So, all right, I'll let you finish that out. On the take-home exam, everyone have that copy in front of them real quick? Take a look at number 2. I give you an acceleration function, just like this, and I give you some information about its position at 0 and its velocity at 0. So this is just like this problem, right? Now the function itself is a little bit harder, right? The integration on that is going to be a little more enjoyable. But then what am I asking for? If a of t is this vector function, right, and I give you this information, then find the distance from that particle to a plane at a specific point in time. So you got something, all we've done is we said, hey, here's the acceleration, right? Here's the position at 0, Here's the velocity at 0. From that, tell me when t is 1, how far that particle is from this plane. So you've got to recover, you've got to figure out this point, right? Like where is that particle at a certain point in time? And then you have to find the distance from that to a plane, which is something we've done before. Distance from a point to a plane. That make sense? That's gonna be a pretty involved problem because the integration on that's not straightforward. I believe that's it. Yeah. Okay. So now we've gone back. We've recovered. Okay. I accidentally skipped that. So 10.7 is now officially done, and we can go back to what we were doing before last week, which was 11.3. We'd start talking about partial derivatives, and remember that's where we have a surface, and we say, okay, if we're standing on a surface, then if we point ourselves parallel to the x-axis and then start to take a step, are we going to go up or down? Or if we point ourselves parallel to the y-axis, take a step, or we can go up and down, up or down. So when we are standing on a surface and we're looking down parallel to the x-axis, that's a partial derivative. That's the partial derivative with respect to what? If I'm parallel to the x-axis, what am I holding constant?
X.
Not x, because I'm moving this way. I'm allowed to take a step this direction, right? And that's the x direction. So I don't want to hold x constant, but I'm not allowed to move this way or this way, okay? So this is going to be the partial derivative with respect to x, which means you hold y constant. Turn this way. Now I'm allowed to walk this way. I'm allowed to change my y, so my y is a variable. My x is constant, all right? And this was what we ended class with. I was showing you that when we take partial derivatives, there's all these different notations for it. And that's what we ended class with, all right? Now, just like in Cal 1, if we have a derivative, well, then we had second derivatives and third derivatives and fourth derivatives, right? So we have the same thing here. We can have second partial derivatives. Now, this gets a little tricky because if I'm aiming this direction, right, parallel to the x-axis, that's the partial with respect to x. And that derivative would give me the slope of the tangent line in this direction, right? But what would the second derivative give me? What do you think it would give you? What did it give you in Cal 1? What did the second derivative give you? It's a concave up or down, right? So the second derivative, the second partial derivative, so with respect to x twice, should give you some concave up or down this way. Make sense? And if we do it this way, partial with respect to y twice should give you concave up or down this way. But because we have two variables, there are also two other partial derivatives you could have. So we could do the partial with respect to x. You do what's in parentheses first, and then you follow it by doing it again. And that would be, you write f xx, and that means you take the derivative with respect to x twice. You could also write f11. You remember what the 1 meant? The first variable. So x, y, z. So 1 would represent x here. And then we also have this notation, this partial, that partial d notation. So let's contrast. These first two are what you would expect. Oh, that's a typo, isn't it? Do y'all see that? That's a typo. 2. I'm glad I looked at that. Okay, so f11 or fyy would mean take the partial with respect to y, then do it again. Now, this is the one that I think is kind of tricky, I guess. So if you write fxy like this means partial with respect to x first, then y, right? So if you don't write it with the parentheses, you write fxy, you have to know you're reading these from left to right. So you go with respect to x, then y. Here you go with respect to y first, then x. So you go yx. Make sense? We're going to do an example, but And then these notations are the same thing. I'll let you look through those on your own. Let's do an example. Find all second partials. So there's only 4 second partials we can have. XX, YY, XY, YX. Those are the only 4. So let's first find the partial of f with respect to x. So remember, that means we're going to look at this problem. We are going to treat all of our what's like constants. All the y's get treated like constants, don't they? All the y's get treated like constants. So what is the derivative of x squared? 2x, right? 2x. And then here, the y to the 5th is a constant. 4 is a constant. So that's all just a constant. So derivative of that is 0. Yes? And then we have minus, this part right here, the y squared is a constant, so I'm just going to ignore it for now. Take derivative of that, and you said negative 30x squared, right? So I'm going to put negative 30x squared, but then we still have that constant, y squared. Is that good? That's your partial with respect to x. Let's go ahead and find the partial with respect to y while we're here. So how does it change? What's the derivative of x squared?
4
Hmm?
20y to the 4th.
Yeah, so this is 0, right? This one right here is 20y to the 4th. And then derivative of this one right here, x cubed is the constant this time. So
20x cubed y.
So minus 2 comes out, hits the 10, 20. We still have the x cubed. It's a constant. Now y to the first power. All right, so I have not found any second partials yet, right? Those are just the first partials. Now let's get the second partials. So what about f, x, y? So that means you do the partial with respect to x first, right? And then y? Well, we did the partial with respect to x. So now if I look at that and take the partial of that with respect to y, what do I get? So with respect to y, that's 0. And then this is all a constant. So the 2 comes out, so just negative 60x squared y. Why didn't I do xx first? I guess it's up to me. I could have done xx first, right? I did xy first. I'm not sure why. Doesn't matter, right? Got to get them all. Let's do partial yx. So that means you take partial with respect to y first, then x. So I'm going to look at this one and take derivative of this one now with respect to x. So what's the derivative of this with respect to x? Negative 60x squared y. They're the same. Wonder if that always happens. I wonder if that always happens. Okay, we got 2 of them, right?
Right?
What's that?
That means they're homogeneous.
Oh yeah, that's, you know what? It is connected to that. You're thinking of diffie q, right? Is that where you?
We learned that like before, but I had no idea what she was talking about. But
Yeah, they're connected. They're connected. Yes. All right, let's do fxx. Okay, so fxx means I want to take derivative with respect to x first, then take that answer, take derivative with respect to x again. So that's this, right? So 2 60xy squared. So there we're just popping the 2 out, right? The y squared is a constant. All right, fyy. So that's derivative of that with respect to y again, right? So this with respect to y again would be 80y cubed minus 20x cubed. That's it, right? Because y is just y, so derivative of y is 1. Everything else is a constant. These don't match, do they? But these do. That's interesting. All right. So mechanically, you understand how to do those 4? Now, Clairaut's theorem. This is not super, super important, but it's in the book, so I'll mention it. It says that, let's say you're given z as a function of 2 variables. So let's say you have a surface, right? If your function is defined on some disk D, so remember our surface lives up here, right? The domain of the surface is down on the ground, right? This is x and y, and then our z's are up, right? So our z's come up like this. Then it says, let's say you have a surface that's defined on a disk. So on the ground, imagine that there's this disk on the ground. Call that D. And all these points in the disk get mapped up to some weird shape up here, okay? Does that make sense? If you take just the points in this disk and map them up into the surface, then you have something up there, right? You have some little piece up here, a patch on top of this surface, or on the surface. It says, so you've got the functions defined on this disk, and this disk contains the point x naught, y naught, right? And this is the important part. You've got this surface, it's defined on this disk, and that point x naught, y naught's in there. It says, and these partials, these second partials, the partial of f with respect to x then y, and the partial with respect to y then x, if they're both continuous. Now, what does it mean to be continuous? It just means that when you take the derivative of them, there's no like crazy division by zero or square roots of negative numbers. As long as that doesn't happen anywhere on this disk, then you can be guaranteed that the partials will match. Partial with respect to x then y at that point will be equal to the partial with respect to y then x at that point. So those two second partials will be the same, just like they were in the previous problem, right? So what were the second partials in the previous problem? X, y, and yx. It was negative 60, negative 60x squared y. See, if we ask ourselves, is this continuous? Then you have to go back to a theorem I showed you all a while back when we were talking about limits. We knew that limits sucked, right? Limits were hard to do of surfaces, but I showed you that we can talk about continuity and that all polynomials are continuous. And this is a polynomial in two variables. So this is continuous everywhere. And because it's continuous, we should expect that these two things would match. All right? Won't always be the case. But if those are continuous, it will be the case. What the hell does that mean? fx, y, yx. I'm going to do the partial with respect to what first? X, then y, then y, then x. Now you could have got this right even if you read it backwards, right? But this one, there's only one way, right? You go which one first? Y, then x, then x. Okay? So let's try that. Let's try that first one, part A. This is going to be a pretty easy one because it's a nice polynomial. So polynomials are always easy to take partial derivatives of. So what is f with respect to x? Partial of f with respect to x. 2x, is this the same problem? Is that the same one? Yeah, minus what? 30x squared y squared, right? So that's your partial with respect to x. Now, what about the partial with respect to x then y? So I'm doing this one, right? So we did that already, right? That was negative 60x squared y. And now let's do partial with respect to y of that again, which would be what? Negative 60x squared. And then finally, the partial with respect to x, then y, then x would be negative 120x. This is just an exercise to make sure you understand the order and the notation, all right? I think you could do that one. I'll let you do part B. All right, Laplace equations are something that comes up in engineering, mechanics, heat dynamics, fluid flow, electric potential problems, these things called Laplace equations. And basically a Laplace equation is just an equation. It's just like if I write x plus y equals 4, that's an equation, right? There's a certain value of x and a certain value of y that I could plug in and I could get 4, right? I get 2 and 2 would work, 3 and 1 would work, right? But it's an equation. A Laplace equation says that, look, if somebody gives you a surface, look at this as a surface, a function of 2 variables, then we will call this right here, we will say that it satisfies the Laplace equation if this is true, right? So you give me a surface and then you're asked, does it satisfy the Laplace equation or not? All right? Does it or not? And to do that, you have to check that this is true. Now, this is the notation you might see in an engineering class, but this is equivalent to saying the partial with respect to x twice plus the partial with respect to y twice has to be equal to 0. If that's true, then that original surface or whatever satisfies the Laplace equation. So we need uxx to be equal to, uxx plus uyy to be equal to 0. So is this surface a solution to the Laplace equation? So it's a very simple check. We have to check, is uxx plus uyy equal to 0? If it is, then it's going to fall into a category of surfaces that have very special properties, right? Okay, so what's ux?
3x squared plus 3y.
3x squared plus 3y squared. All right, that's uxx. What's ux? I'm sorry, that's ux. What's uxx? 6x. That's it, right? That's it. Okay, now, what about uy? Partial of u with respect to y? 6xy.
And 6x,
So, and then partial again with respect to y, you get 6x. Right? Now, if we add these up, do we get 0? No. We do not. Right? So this right here for us is 6x plus 6x. Does that equal 0? No. Right? Well, it could, right? If x was 0, but that's only one. It only satisfies the Laplace equation at one point. To satisfy the Laplace equation, you have to satisfy for all x and y. Okay, so the answer here would be no, right? So any surface that satisfies the Laplace equation, they behave a certain way. And it's used in harmonics. Like you have a whole category of functions that act a certain way so long as they satisfy the Laplace equation. One way you could look at it, maybe this might help. I don't know if this is going to help. Let's say I have a surface, right? Then if this is x and this is y, then the partial with respect to x gave us a slope of a tangent line this way, right? Slope of a tangent line. Partial with respect to y, slope of tangent line this way. Partial with respect to x twice gave us concavity, right? This way. And partial with respect to y twice was concavity this way. So to satisfy a Laplace equation, what are you actually saying has to be true? If I say that uxx plus uyy must be 0, then I'm really saying uxx equals negative uyy, right? If I move one of those over to the other side. So that means whatever my concavity is in this direction, it's opposite if I'm in this direction. So it's like if this one is like concave down, like maybe it's concave down, it has like a curve of, let's say, like -2 would be concave down. Then if I face this direction, it's +2. Does that make sense? So you have like this saddle kind of happening, like this. in this. Yes, but it doesn't have to be the same ratio the whole time. I mean, sorry, the ratio has to be the same, has to be -1, but they can be different values. So you can have more of a curve in one place than you do in the other. All right, I'm going a little off topic, but that's what's happening there with the Laplace. And Laplace is not the only one. There's other kinds of classifications of functions. All right. Well, again, like we did in Cal 1, we took derivatives. We took, first derivative, second derivative, right? Here we had this new idea of like partial derivatives holding one variable constant. Well, now we move to implicit differentiation. And that's, if you remember back from Cal 1, if we had an equation like 2xy minus, let's say 4y squared equals sine of y, if you want to define y prime here, it's difficult because you can't solve for y. Right? You can't isolate y by itself, so we did implicit differentiation. And that means we said, okay, we're going to differentiate the whole left side, let's say with respect to x, and then we're going to differentiate the whole right side with respect to x, and then you had to use product rule, chain rule, everything was in play, right? Does that ring a bell, or should I work through that one to get us ready for this? What do y'all think? No? We're okay? All right, so here, if I give us an equation, notice that this equation now contains 3 variables, x, y, and z. And what we're saying is that you cannot easily solve for z. If I could solve for z, like if I could do this and do a bunch of algebra and get z equals, and then this side over here just has x's and y's, then I would have f of xy over here, and then I would just do the partials that we were just doing, fx, fxy, whatever, right? But if we can't do that, if we cannot isolate z, we should still be able to talk about the slope of the tangent line in certain directions. Do y'all remember what types of curves this helped us with? Like look at this one right here. That's a circle, right? Radius 2. In Cal 1, we found that we could find the slope of the tangent line here, anywhere on this circle. But see, this curve is not a function, right? It fails the vertical line test. But in Cal 1, we could still find slopes of tangent lines. What implicit differentiation for us here in three-dimensional space means is that let's say we have a surface that is actually not a true function. So maybe the surface wraps around. So maybe it's like a basketball or something like a weird blob, but it comes back around on itself. So it fails that vertical line test, so to speak. That make sense? Can we still find the slopes of tangent lines? Yes, we can, but we have to use a different type of differentiation. We use implicit. So let's try and see if we can get this first one, part A. I'm taking the partial of z with respect to x. That's what I want, right? I want us to find this. So that means I'm doing a partial derivative with respect to x, right? Which means I'm holding which variable constant? Y. And z, we are going to assume, is a function of both x and y. So in this problem, whenever we're doing this, we treat x like a variable, we treat y like a constant, and we treat z as if it is a function of x and y. Let's see how that plays out, all right? So what would I do if I have an equation? I just start differentiating, right? Both sides with respect to x. So what is the derivative of this with respect to x? Just 3x squared. So I start out, I get 3x squared. Great, okay. Plus, now what's the derivative of y cubed? 0, because I'm holding y as a constant. Plus, now here's the tricky one. What's the derivative of z cubed? It is not 0. We're not saying z is a constant. So 3z squared is what we, I think, would naturally feel, 3z squared. But then there's one super important thing right now. Times the derivative of z itself.